Welcome to H2O World. And so for the next 20 minutes or so, I'm going to try and give you guys a high-level architectural overview of H2O. The goal here is not that you understand how it works, really, but that just come up with the feel of what kinds of things are possible and why, so that you can look at your own problems that we're not currently solving and decide if H2O can be made to do that, and maybe go to the next step and hack something in yourself. And if you're interested in hacking, we have a hacker's corner over here where I'll be hanging out all day to help people code inside H2O, presumably, hopefully with some new math that we haven't thought of, that we haven't invented, that we don't have working right now. That'll be your own unique contribution to things. So, OK, here we go. Right, 20 minutes. And then, right, on stage all day, all kinds of tool user things that you're going to learn about, use cases, experiences, how to do things. And then if you're interested in hacking, the hacker's corner, and come and go as you feel. OK, so what is H2O? Sort of at the core, it's almost anything you want to do on big two-dimensional tables. So anything you can do in Java that reads or writes a single observation, or maybe some nearby observations as well, and possibly computes reduction along the way, can be done easily in H2O. And the speed is typically the data volume you have divided by the memory bandwidth of your entire cluster. So this is actually really fast. Often passes over all your data are done in handfuls of milliseconds, even for gigabytes, a second for a terabyte, so fast. And you're limited to data that looks like numbers and times and strings and a couple other things like that. But the length of the table is basically limited by memory only, and we definitely test at the high billions range. So I'm going to have one slide here. Inside of H2O, there's a key value store. Follows the Java memory model. Anything you put on one node, you can get on another. And we use them externally to point to results, data sets, models, anything that you're going to talk to it from R. You'll hear people talk about a key. That's a pointer into H2O, and any node in the cluster from that key can get whatever thing that you're talking about. And you can put data sets in, refer to them by key, and pull them back out, and models in and out, and things like that. Internally, we use the same key value store to all kinds of stuff, including hold on to the big data. And that's all I'm going to say about the KB store. OK, so what can I do with H2O? So here's a high-level picture, and I'll show you some examples. The main way we code, it's not the only thing we can do, but the main thing we do is this MapReduce paradigm. A lot of people immediately think Hadoop MapReduce is not related to Hadoop MapReduce. It's really the theoretically clean MapReduce. So map from type A to type B, where the input is billions of rows or observations. And the output can be both a big and a small output. For a small output, you have to have a reduction operator, which takes two type B things and makes one. And for a big output operator, you're going to put it back into the cluster because presumably big output is too big to fit on one node, so it has to be a cluster-wide thing. And the ultimate coding style, again, this is a little bit of Java. You extend MapReduce, override map and reduce from an MR task, and say, do all, and it will just run in parallel across your thing. So here's an example of exactly that, a MapReduce task. So again, don't absorb or think you have to absorb everything that goes on here. This is just a high level, I'm going to gloss over fast. Make an instance of MapReduce task, override map and reduce, and do all, and bang, that ran parallel distributed across your cluster, milliseconds per gigabyte per high gigabyte count. In this case, the type A is a double, and type B happens to be a double as well, but it can be something more complicated. Here, my type A is a pair of doubles, and my type B is the Java POJO, the plain old Java object, LR task, the first pass of LR pass 1 here. It's the first pass of linear regression. So it's a couple sums and a sum of squares. It's pretty straightforward. But we can get maps that get really complicated and have like large internal arrays holding on all kinds of things and deep structure. You can get really complicated stuff in there. Many of the algorithms go there. Here's another simple case, just doing a filter. If certain test passes return a 1 or a 0, and then you can count them. And you immediately get counts of things that pass a filter. And as soon as I can filter and count, I might want to collect a set. So here's the same thing. And of course, I don't have a flip page, so my color transitions aren't going to work so well. All I'm doing here is saying I have a large output result. People who pass a filter go in the result. People who don't. At the end of my pass, I will have collected some subset of billions that might still be billions in size distributed around the cluster. So you can subset and play games with different sets of people. Here's another instance for a MapReduce where I'm computing into an array of car ages here, simply looping over the data and saying, compute a group by of your age in the car and count the number of people who have cars at whatever ages. There's a bunch of utilities for doing things with arrays, and this is an element by element add, similar to a SAXB for people doing BLAS kinds of things. All this code runs as is, like across the cluster at this giant speeds. There's a little bit of thinking here about single-threaded versus parallel. The paradigm is you write single-threaded code. The actuality is it's going to run parallel. So in this case, my map made a new object that was local to the thread running that map, but there's lots of maps floating around. So I have lots of these arrays with results running around, and then the reduction is going to fold them all together. Here is a distributed hash set being used to count unique visitors, where the hash table is collecting the uniques by folding together duplicates in the hash set. And the reduction is just folding two hash sets together from across the cluster, and bang, I got unique counts. So let me skip along here. OK, so the kinds of things that we write in the Java code, the limitations are, if you do I/O, it's I/O local on the node. So if you do like system.out.print, that node prints, and that node prints whatever it's doing, but they're not necessarily all on your console, right? So no machine resource allocations that are local to one machine are going to work because that'll be on the one machine and not distributed, right? No new threads, no locks because it's a distributed locking. Doesn't make sense. System exit will, shoot a node in the head. It's probably not what you want. Global variables become node local. And for small things that are in read state, you just throw them in the constructor of your Java object, and they get cloned around the cluster for you. For large things, you're going to reuse the reduction, and they're going to keep folding them down until you get down to a small global result. For big objects, they have to go in and out of the big data distributed store, the giant distributed arrays. The strengths, on the other hand, are pretty interesting. It's actually a very straightforward coding paradigm to write to. You really do think about it as a single-threaded coding style when you're writing these maps and reduces. And it will run on millions and billions of rows and thousands of cores without any further effort. No concurrency issues at all. And there's no knobs tuned like you might see in some of these other systems for GC or CPUs or network or data placement or hot locks or hot block. None of that. That all just works. OK, so here's the high level. This is the intuitive feel for which, this slides work better if I could flip, but I don't. OK, so I'm going to say, make me a new MapReduce task and do it all. And what it means is on some JVM in a corner, I said, make me a new object. That's a blue guy. And then when I say do all, he says, well, I got a lot of data floating around. Everyone needs to touch it. So I'm going to clone an instance on two JVMs. There's a log tree fan out. And those friends are going to tell their two friends until everyone's got a copy. Then if I dive into a single node, it's classic fork join, divide and conquer, recursive descent kind of approach. I got chunks of data, lots of them. I show 4,000s, tens of thousands, 100,000s, lots of chunks of data. So the map task says, I need to go run this across all the data. So I'm going to clone myself, pick up another CPU core. Though that second core and the first core will both clone again, and clone again until all the cores on my box have all cloned enough tasks so that I get a task for every chunk of data. And then I do that map call. Here, one more. Here, I do the map call. And I put in those Java objects the result of the map, the output from A to B. So the A is your data, the purple stuff, and output is the B stuff. And that's your map from A to B, but run parallel and distributed around the cluster. Once I've got my Bs ready, I start doing reductions, pair by pair by pair by pair by pair. They roll up again, they roll up again, until I have all the work on one node done in one Java object. That's my B. My big data output's already been put back into the cluster in the JVM heap already. But the small data keeps getting reductions, and the reductions go back across the cluster, pair by pair again, but now in a log tree roll up through the cluster. People push results uphill, 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 until the final reductions back in the original instance, and I have my type E. The runtime of this is data volume through your memory bandwidth, plus a log size of your cluster, network hop, back and forth. And for most things, that turns into milliseconds per gigabyte for high gigabyte counts. Bigger cluster, you're going to get more gigabytes through because you got more memory bandwidth, and the log tree goes very slowly. But definitely, it's fast. OK, so that's the high level. This is how the paradigm works. Here's a little bit of how the code looks internally, of how you think about it. The main thing you think about is columns of data are like a distributed array, a giant array, more than 1 billion elements, more than 2 billion elements, more than a Java int's worth of elements. So the length is a long, not an int. You can do at and set. That's the same as get and put, whatever. It's read and write. It's single element, random access. It's fast. There's a missing element notion for all data types. And of course, variable size means I can append in parallel and concurrent around the cluster if we're getting into the append mode. And I don't know why, there it goes. So if I'm looking at a single vector, it might be very large, as I just mentioned. Under the hood, by the way, it's compressed very heavily. It's invisible to you, except in terms of how much data you can fit in the amount of RAM. We typically see 2 to 4x better than gzip on disk. So the compression is actually really good. And that turns into more speed because the compressed data is what goes through your memory bandwidth, memory bus. The data is distributed across the cluster this way. Here's 4 JVM heaps. And every JVM has a slice of that giant array. And of course, you don't have one column. You have a lot because you're doing something with real-world data. So here's a data frame. This is very much based on an R data frame. That's the kind of mental model. It's cheap to add and drop columns. So mix and match. Throw columns in, throw columns out, make a new column, add it on, take it off, whatever. And the columns are all carefully aligned so that when you go, when the code runs, all the rows for one observation are all in one machine. So there's no cross-network traffic to go talk about a particular row. So you get a collection of these distributed vectors, but they're all carefully aligned. So the random access on any row is possible, but linear access through a row is at memory bandwidth speeds. And then as I mentioned before, the columns are actually broken up into these chunks. A chunk will not span a JVM heap boundary. It's one JVM, typically 1,000 to 1 million elements. It's there for a unit of compression, unit of parallel access, unit of good data load balancing work. But otherwise, you won't see it. The chunks are, like I said, carefully aligned so that any one core will work on a set of chunks all at the same time by itself as single-threaded. So no other JVM's messing with it. So he'll roll through all those, and I get a nice fine-grained amount of work involved, but it's enough work that I don't have control overheads to launch threads. And of course, it's not just one chunk going at once. It's all your cores grabbing all your chunks all at once and running parallel across the cluster. OK, so there's this taxonomy internal to H2O, but it matches R to a lot of extents. So there's a frame, just a collection of vectors, distributed giant vectors, where a vector then is internally a collection of chunks. These are almost invisible unless you're coding deep in the core of the system. And they're a collection of 1,000 to 1 million elements, and that's my unit of parallel access and my unit of compression. And within a chunk, the chunks are elements, raw data elements, conceptually, typically a Java double. But how that's actually stored in memory is up to the compression strategy. And then I say a Java double, but there's some flex there. So you can have both strings, and you can have time numbers, and you can have categoricals and enums and stuff. And so the actual representation might vary a little bit. Depends on what kind of data is stored in that array. The arrays are all single type per column, though. You can't mix enums and strings or real numbers and time. You have to pick one type for the column. OK, so that's actually that was my blazingly fast blow through in the architecture. Like I said, there won't be any quiz on this later. But when you hear these terms come up later in the day, you have something to hang your hat on or hook your brain onto. So when we look at the system sort of from the outside going in, a lot of what happens here today will be what I call no distribution coding. You're going to talk about whole algorithms or whole units of vector math operators. REST and JSON is the way to talk to the system here. You're going to load a data, run a logistic regression, get some results back and forth. In this mode, you won't see the distribution except to know that it's fast and it's out there and it's holding your big data. And you often will talk to the system with something other than Java. It'll be R, Python, web-based, clicky in the browser, or Bash and curl scripting, however that goes. You go in a layer, you see the Java. And then that's the simple data parallel coding style I just blew through really fast. It's a MapReduce style, works really well for anything that's looks like very dense linear algebra, works reasonably well on sparse data up to a point, but the coding style is just very friendly. You just can say for each, do all, and write some code, and bam, it happens. And then you can go under the hood even more and play with the KV store directly and do more exciting stuff that doesn't look like dense linear algebra things. So summary here is that most simple Java just works. We have a lot of programmers hacking, including some first-time Java programmers who are actually mathematicians, who have found it very convenient to write. And sometimes the maps can be thousands, tens of thousands of lines of Java code, and it all just works. Reading and writing is basically the same speed as a plain Java array load or store. You have to say at and set instead of square bracket to access it, but otherwise, it's just as fast. Typically, we're memory bandwidth limited, so zoom, right? And you can do fancy stuff with conflicting writes, but you got to be like a good systems hacker head to want to go there. But it will work and do the expected things. So that is the end of the architectural overview. So so question was, we're a SQL Server shop. We have a lot of data stored there. How do we get it into the system? Yeah, OK, so right now, the primary mode of pulling data in is a CSV file from any number of variety of sources, local drives, HDFS, S3, however. But it's definitely a CSV. We have plans to do a JDBC driver, which would let you do direct parallel ingest from your parallel database. Right now, that's on our list of things to do, and we're looking for resources to go do that. And I'd love to have somebody who wants to hack on that, by the way.
Is it possible to make your own data ingester?
Yeah, so a data ingester takes about a day to write. Basically, we need open, close, seek, read, and write as the only operators. And then it's very straightforward after that. You just grab like HDFS or NFS reader and clone it and replace those 5 operators, and you're done. And it just works.
Do you require HDFS as an underlying file system for memory overflow?
OK, so do we require HDFS as an underlying file system? The answer is no. And then you also mentioned memory overflow. So let's go the 2 different directions here. So ingest any one of the things I mentioned before, S3, local disk, browser upload, URLs, URIs, however. Then there's an overflow case where you've got more data than RAM. We will spill to whatever we're told to spill to. By default, it's typically local drive/temp. But you can spill to HDFS. The risk there is you went from memory bandwidth speeds to disk speeds. So if your data you're loading in is something you're mostly not going to touch, then it will spill to disk and stay there on disk, and it's all good. But if your algorithm is going to like sweep over all the data again and again, you're moving to disk speeds now. And at this point, you lost the big advantage, and the right thing to do is actually downsample the data or up your cluster, get more RAM.
OK, here's a question.
You want to? I'm flipping to the new speaker. Yeah,
One
I'm
question.
getting there.
All right. So 2 questions, really. One is, what is the largest amount of data you have seen in your real-life implementation, which you have supported? The second one is, one of the slides read that if the width is less than 1K, is better for performance, right? If it is more than 1K, the performance deteriorates a little bit. So what do you suggest? What are your best practices to, if I have lots of columns,
OK, so so I'll answer the second one first because I heard it and I was still catching up for the first question. So the column count, we're definitely optimized for tall and skinny, where skinny means 1,000 or less works really well. 10,000 or less definitely works. Some algorithms work better, some work worse. 100,000 or more starts to hit to the point where things aren't going to actually work how you want. So that's the limiting on the column count. We have in plans and architecture design to go for the other direction, but that's definitely not something we've implemented right now.
Is it because of swapping?
No. It's the loops are parallelized the wrong way. So the answer when you go to the million columns and you're typically short data, you want to parallelize going this way, and we're parallelized going this way. So we have to rotate the loops 90 degrees, and that's the piece of engineering that's a big chunk. OK, and you had a first question?
Yeah, what is the largest data you have seen?
Oh, I think we've played around with a couple terabyte sets. I think. These are like many billions, but I don't know. It was like versions of the airlines data set upsampled, and there's a couple ones that were like security, network packet flows and stuff. But I want to say tens of billions on that order of magnitude. Okay, another question here, and at some point we want to flip over. Okay, let me take one more question, and then we're going to flip speakers.
One of the slides said that it's mostly memory bandwidth. One of the slides said it's mostly memory bandwidth limited, but that in some rare cases it's CPU limited, and I was curious for an example of the CPU limitation
Right,
case.
right. CPU limitations come about when we have to do math work over the cost of moving the data through the memory bus. So if you look at a modern x86 and you look at his amount of core cycles he can burn versus the amount of memory bandwidth he has a lot of cycles left over to do crunching, but not an infinite number. So if I shove data through the memory bus and you're piling through these gigabytes, it's really cheap relative to the memory cost to do some decompression. So I burn, 2 to 8 cycles per element to decompress. And I probably got 20 or 30 cycles more, which is enough for dozens of FP adds and multiplies and games like that. But you can exceed that, and then you become CPU bound. So if I'm doing like a gram matrix calculation, and I'm doing feature squared per row that comes in, then the row grows as the width of the feature count, but the work grows as the square. And at some point, I exceed the memory bandwidth cost versus the FP doing feature squared math calculation, and now it's CPU bound. So like I said, 1,000 columns works well. One of the games there is a lot of the algorithms will do. We'll do a gram matrix, which is this p squared calculation. But if p gets 1,000, then you're doing 1,000 by that. You're doing 1,000,000 flops per line of data that comes in, and you can become CPU bound. When you go to 10,000, that kind of style now goes to 100 million flops per row that comes in, and it quickly becomes very CPU bound. Okay, so with that, let me put a stop to questions. I will be in Hacker Corner all day and happy to answer more.